find the curl of 3xyi plus z squared yj plus xyzk. And there's several things listed here. Among other things that this problem does is it reminds us, oh yeah, we have this other notation involving I, j, and k. Now it takes a few minutes to work it out. Has anybody had a chance to work through it? D? D is the right answer, yes. Good. Now, there are, of course, a few tempting things. You might have remembered last time we talked about if you take the curl of the gradient, you get 0. You take the div of the curl, you get 0. That doesn't mean if you take the curl of the curl, you get 0. If you also just take the curl once, and so remember curl, you take, it's the cross product. So set it up as a matrix. You've got your I, j, k vectors, your partial derivatives, and then the individual components. And you'll notice that the one curl shows up as an answer as well. Again, very tempting, but we know you must curl twice. And so you end up with the expression y, 3 plus x minus 2y, 2z. Not really any surprises. It's just a matter of patiently working through. All right. Any questions on this one? Okay. Well, our thought for the day, courtesy of Eleanor Roosevelt. You gain strength, courage, and confidence by every experience in which you really stop to look fear in the face. You're able to say to yourself, I lived through this horror. I can take the next thing that comes along. You must do the thing you think you cannot do. And, this goes back to things we've talked about earlier in the semester. You have to learn to get out of your comfort zone. You have to push yourself. Be comfortable with being uncomfortable. That's the right way to say it. And it also reminds me a little bit of our saying from Dune. I'll let the fear pass through me, and after the fear has passed, I'll look back. Only I will remain. You say, look, you're capable of more. You can do a lot. All right. Now, what are we learning today? Well, we're learning about line integrals. So, going back to one-dimensional integrals. Now, we did integrals in Calc 1, and we know how to find integrals in Calc 1. At least we have a pretty good sense. Integrating from a to b, f of x dx. So there's some function f of x dx. I go between a and b, and I'm finding the total. Oftentimes, when we start, we think geometrically, oh, it's like finding an area. Well, now we're going to go to a higher dimensional setting. So we're going to integrate along a curve f of xy ds. Now, the way I'm thinking about this, when I write this out, is I can think about it as an area in that I have a curve, and there's like a curtain that hangs above that curve. But it's a curtain of varying heights. And so depending upon where I'm at, it might be taller, it might be shorter. And I'm still saying, okay, what's the total area inside of that curtain? Now, there's a couple of things that seem sort of out of place, but let's talk through it. One thing is, this looks like it's a multivariable integral, because you see this f of x comma y. But what that's telling us is f of x comma y says that there's this surface, and I haven't plotted it, because I'm not very good at drawing surfaces by hand. But the point here is that if I have a point down here in the plane x comma y, the height f of xy, that's telling me how tall my curtain is at that point. So it's not a multivariable integral. In fact, there's a good clue is you count the number of integral signs. So the number of integral signs tells you the dimension of the problem you're working on. When you see a 1 integral sign, it says it's a one-dimensional integral. So there's only one thing which will vary. We'll go back and do 2-dimensional integrals and 3-dimensional integrals as we go along, but for today and next time we're focusing on 1-dimensional integrals. All right, well, how do we find such a thing? Well, we have ways, and they'll sound very familiar because it's the thing we always do with integration. We're going to break what we're looking for into small parts. We're going to find the contributions of each part, and then we're going to add it all back up. So, how do we go about that? Well, we're going to think of taking our curve, and we're going to break it up into lots of little pieces. Now, the more pieces you have, the more accurate your estimate will be, and of course, the idea is you let the number of pieces go to infinity. There's a few things, some callbacks from previous in the semester. We have S, which is the cumulative arc length function. So this S right here just says it's a little bit of length downstairs. So you can imagine this downstairs is the ds, and then the f of x, y is the height. Height, width, area, life is good. Okay, so we know how to find the cumulative arc length function, or at least we know how to compute it. It's the square root of x prime squared plus y prime squared dt, essentially. And if it looks like, isn't that the arc length formula? Yes, it is the arc length formula. Same formula. And so if you were just integrating 1, if you integrate 1 ds, that's finding arc length. But now we don't have to integrate 1 ds, we can integrate other things. Okay, so here we go. We have our curve. We're going to tie it to a parameterization, x of t, y of t, where t starts and stops at a and b. So we can say maybe the start we'll put here is t equals to a, here's t equals b. Then the total of whatever you want to call it, we'll call it area for now, is you add up, break it into pieces, the height times the width. And then we say, well, but how do we find these pieces? This is where the parameterization comes into play. The x's and y's are being parameterized by t. So we become x as a function of t, y as a function of t. Delta si, again, can be expressed in terms of t. And then we say, okay, let the number of pieces get big, and instead of a sum, we get an integral. Integral a to b, f of x of t, y of t, square root of x prime squared plus y prime squared dt. So we can convert this integral along a curve to an integral that we're more comfortable with, an integral from a to b, like something from Calc 1. All right, good. And hopefully it's not too bad. There's one part that you might be like, uh-oh, I see trouble ahead. This looks like it could cause trouble. And yes, but also no. In the case that we are going to care most about, it's actually good that it's there. But that's for later in today. All right, so there's the theory. Are we ready for practice, or do we need to, any questions on the theory? So the punchline is, if you're integrating along a curve, use the parameterization to write it as an integral of a single variable, and use your Calc 1 skills. All right. Well, in that case, here we go. Find the integral along the curve of x squared y ds, where the curve is 3 cosine t, 3 sine t, and you go between 0 and pi over 2. Now, I realize I don't think I said something, which I probably should have said, is there's this suggestion down here which is to use simple parameterizations. When you have a curve, there's oftentimes multiple ways to parameterize it. The integral doesn't depend on your parameterization. Given that it doesn't depend on your parameterization, use simple ones. Why? Because we like ourselves. And we want to make life easy. And so, if it doesn't give you a parameterization, find the simplest one you can. All right, but this time it gave you a parameterization. Now, we don't need to know, but we might as well plot it. 3 cosine t, 3 sine t, t going from 0 to pi halves. Where is it moving along? What's the basic curve shape? So roughly speaking, x is like cosine, y looks like sine. What kind of thing has x is the cosine, y is the sine? Circle. What does the 3 do? Yeah, it's a bigger circle, right? Radius 3. So at time 0, we're here. And at time pi halves, we're here. And we're going between the two. So that won't enter into play, but I'll just make that note. Now, I will comment that the way this is written, we don't care about the direction we travel along the curve. So right now, we're going in that direction. So we start at time 0 at x equals 3, y equals 0. We end at time pi halves at x equals 0, y equals 3. But it won't change the answer if we went in the opposite direction, because we're just finding the area above the curve. By the time we finish today, we'll have things where it does matter. So I just want to point that out now. All right, so what's the idea? Well, most of the energy that we're going to expend is going to be, can we simplify ds so that we can have success? So we'll work on that. ds, that's the square root, x prime squared plus y prime squared dt. Okay, so in our case, what is x prime squared? Or what is x prime? Let's just do that. Negative 3 sine t. Good. It's negative 3 times sine t squared. What's y prime? 3 cosine t squared dt. All right. Now, if they've been nice to us, hopefully they'll give us something we can work with. Okay, so we have the square root of 9 sine squared plus 9 cosine squared. Does that simplify at all? What does it become? 3, right? Because you can factor out the 9, and sine squared plus cosine squared is 1. And of course, square root of 9 is 3. So it's like, nice, it's 3. Okay, so the integral along our curve x squared y ds, using this parameterization, well, we have our a and our b. So I'm just going to mark that's a, that's b. This is our x. This is our y. And now you just sort of played the matching game. Oh, and this is our ds. All right, so we have integral 0 to pi over 2. So we're using our endpoints for time. For x, we replace x by what's in the parameterization. 3 cosine t squared. For y, use what's in the parameterization. 3 sine t. And then for ds, we use 3 dt. Okay, so we got 3 squared, 3, 3, it's a bunch of 3's. Altogether, 81. Integral 0 to pi over 2, cosine squared t sine t dt. All right. Can we integrate cosine squared t sine t dt?
No.
Not right away, but some people have suggested u sub. What's a good substitution to make? Yeah, so cosine is a great substitution because notice it's cosine squared. So oftentimes when you're channeling your inner Calc 1, you're like, is there a function on the inside? So cosine's inside a square function, so that's a good candidate to make a substitution. So if you let u equal cosine, then you get negative sine t dt is your du. And we can move the negative across. That says sine t dt is negative du. So negative 81, the negative coming from that negative, integral cosine squared becomes u squared, and then the sine t dt became the minus du. What about the bounds? At time 0, cosine 0 becomes 1. At time pi halves, cosine pi halves becomes 0. Now, if you don't like the bounds being out of order, and some people don't, what can you do? Flip them and then got to negate. But we already have a negative in front, so hey, that works out pretty well. All right, I'm feeling like we are going to succeed on this one. What's the integral of u squared? U cubed over 3. So we have 81 times u cubed over 3. Evaluate from 0 to 1, giving us a grand total of 81 over 3, which is 27. All right. No big surprises. What about 3 dimensions? Can we do something similar where we have a curve in 3 dimensions? Yes. You might say, but do I think about it in terms of area? Probably not. But of course, you don't have to. You can just accept it. We'll give some motivation of what you can think about it as. One thing you can think about is like a density. So you can think your curve as a wire. But it's not a wire with constant density. Depending upon where you're at in space, it might be thicker or thinner. And so if you integrate density, what do you find? Mass. So it can be thought of as like, oh, I'm trying to find mass of a wire as one example. So what do? The same thing. You rephrase this in terms of a parameterization for C. So then everywhere you see x, y, z, you put in the corresponding part of the parameterization. The ds is the same kind of thing we had for arc length for a 3-dimensional curve. All right. So here's the problem. Find the integral along C of x plus z ds, where c is cosine t sine t t, and t goes from 0 to 2 pi. 2 root 2 pi squared. Anybody else get that? Okay, good. Because that's what you should get. All right. So you take your curve, you find your ds. In this case, you get something which is reasonable to work with. And, well, ds just adds a factor of root 2 and cosine and sine. And the nice thing here is the sine ends up actually completely going away. Well, that can happen. No worries. No worries. All right. So line integrals. Now, we're going to do a little bit of work here. And, all right. So we're going to talk about work. So work, when you start talking about work in physics, you often say, well, work is like force times distance. And that's just a very simplistic version. But then you say, well, you start getting more complicated. And you say, well, work is always a number. It's a quantity. It's a measurement. But force is a vector. So in other words, there's a direction implied. And so what we do is we say, well, we change our formula. So it's not force times distance. It becomes force dot product with, and then instead of distance, we call it displacement. So there's the dot product going on. Now, to get some intuition about why we might have a dot product, we'll start with something which you may or may not have experienced. So imagine, if you will, you have a car. So as you see, this is a car. That's, my drawing class paid off. And if you have a car, especially an older car, you might have experienced your car running out of battery or something, where your car no longer functions and it's in a very inconvenient place. And so you want to move the car. So you get some friends. And of course, you have a lot of friends, so they start pushing from behind. But now there's so many people, some have to push from an angle. Now, are they all as effective in moving the car forward? No. What happens? Well, the people directly behind, all of their force moves to having the car go forward. But from the people pushing at an angle, some of it has the car moving forward, but some of their force is being essentially wasted. It's not helping contribute to work. So when you do this F dot D, you're doing a projection. Now, of course, later on, you might see an art history major jump in and say, I'll help too. Now, what's happening with their contribution? Nothing. There's no work involved, just like their future career prospects. Now, so I should add that there is actually only one art history major on campus, one person who has an art history degree on campus, and it's my dean. So don't tell him I said that. So all right. So okay, so that's why there's the dot product involved. So that's why that shows up. Now, the idea that we're going to think about is to say, well, suppose we want to compute a total amount of force. So I'm moving something along a curve. So you can think about I'm perhaps pushing a box along a curve where I start at some point and I end at some other point. So here's my curve. And I want to ask the question, what is the total amount of work that's done? Well, it can happen that the amount of force might vary. So for example, you might have a place where you have to exert more force and places where you might have to exert less. You also have to keep in mind that how do you compute work? It's a force dotted with a displacement. So we do what we always do, which is we chop things into little pieces. We say, all right, let's think about our work. We're going to find it by saying, let's find the work if we move just a little bit. And then add up all those little bits, and that's our total. So that's what's going on. Work is approximately the sum. At each point we have a force, and now we have to have a displacement. So the way we find it is we say, at a given point, I need a direction, and that's when the orientation comes into play. So here, orientation matters. So I'm going to imagine I'm moving from this is the start, and this is my end. So now I have a direction, and I have a motion. So I can talk about the tangent vector. So t, this is a direction. What is delta s? Well, that's a small amount of distance. The direction and distance together gives the vector, the displacement for that small piece that we move. And so it's really F dot the displacement added up. Okay, so that's the work. And now we're going to talk about notation for a few minutes. All right. Not the fun part, but so suppose we have R of t. We're going to use R of t to represent our parameterization. So x of t, y of t, that's our two-dimensional parameterization. Everything we do here can generalize to 3 dimensions, but we'll start in 2D. How do you find the unit tangent vector? Well, how do you find a tangent vector? You take the derivative, r prime of t. And you say, okay, r prime of t, that points in the direction of motion. Essentially, it's the velocity, if you will. Now, it's the right direction, wrong length. So you have to make it a length 1 vector. So, to make a vector into a length 1 vector, divide by the magnitude. And that gets us the original derivative is the x prime, y prime, and then divide by the magnitude of the square root. Right? That's the square root, x prime squared plus y prime squared. And now at this point, it's like, oh, we saw a square root of x prime squared plus y prime squared earlier. Does that mean something nice is about to happen? Well, if you take t ds, this is our t, here's the ds, what do you see? The square roots go away. And so, that leaves us with what we call dr, and unfortunately this is where there's like 3 notations for the same thing. And it's just individual derivatives, x prime t, y prime t. Sometimes we'll just say the x prime t dt we call dx, y prime t dt we call dy. And in general, we say, all right, if we have our force, m comma n, then all 3 of these are different notations for the same integral. F dot t ds, f dot dr, and this is m dx plus n dy. So where we think here's the dx, here's the dy. All of them can be thought of as computing work, where we move along a curve. All right. Our favorite one, and the one I prefer, is the last one. We'll talk about how to use this notation. Keep in mind, orientation matters. Why? Well, what happens if we flip the direction we go? So if we go from start to end, but we flip, now we go from end to start, how does that change things? It changes the sign. Why does it change the sign? Because your tangent vector now points in the exact opposite direction. So it has a sign involved. There's an orientation involved. Now that might seem annoying, but that's good news, because we want signs involved. Orientation mattering says, fun stuff can actually happen. And for instance, we can start doing some fundamental theorem of calculus stuff, but that'll be coming up in the next lecture. All right, so let's try some of these. Any questions? All right. So we're going to do 2 computations here, where we're going to compute the same integral, where we start at the same point, which is the origin. We end at the same point, which is at 2, 2, but we go there in different ways. We just want to compare. And so I'll do one of these, and then after I do one, I'll let you do the other one, and then we can compare the results. Now, before we start, I'll do the one on the right here. When you're setting these integrals up, what you do is you first say, look at the parameterization. And when you have it in this form, you say, okay, you get x's, y's, dx's, dy's. If you're in 3 dimensions, you might have z's and dz's. Everywhere where you see an x, replace it by the x of t from the parameterization. Everywhere where you see a y, replace it by the y of t from the parameterization. Everywhere where you see a dx, any guesses? It'll be x prime of t. And dy becomes y prime of t. All right. And if they don't give you a parameterization, you have to come up with one. So make it nice. Be nice to yourself. So now on this curve, you might notice there's a little bit of a very sharp turn. So what can we do? Well, we'll split it into two pieces. I'll call it curve 1 and curve 2. So the idea of integration says split into many parts. I'm just saying split into two big parts. So let's talk about curve 1. We want to find the parameterization. So our x of t, y of t. So we need to come up with functions for x and y, and we need to come up with the times. So if we're thinking about a particle moving along here, what's true? What's something that's true? Y never changes, right? It's always the same y value. So what y value is there? 0. So that's something 0. Now, what is x? Well, it changes. It goes from 0 to 2. So I need a function that starts at 0 and goes to 2. Now, there's a few things we can do because we actually have several toggles to play with. Namely, we have the bounds and we have the function. So we could do 2t, because that seems pretty easy, from 0 to 1, or we could just do t and 0 to 2. Both are perfectly valid. Let's try just t by itself. All right, so there's our parameterization. So now let's do the integral along C1 of, write it down, xy squared dx plus xy squared dy equals integral. And now we use the bounds for our parameterization, 0 to 2. X becomes t, so we have t times 0 squared times dx, which is 1, plus x, which is t, times 0 squared times dy, which is 0. That's what we're integrating dt. What will that integral give us? 0. Yeah, hard to recover from multiplying by 0 squared. All right. But that's only half of the story. We have the other half. All right. So now we'll do C2. So we have x of t, y of t equal to, all right, what's true along C2? X is a constant. What constant is it? 2. All right. What do we do for y? So y is changing, right? It starts at 0, ends at 2. So what do we put here? And there's not one right choice. There's many that we can pick. I like t because t is simple. If we choose t, what are our bounds? 0 to 2. So the integral C2 xy squared dx plus xy squared dy equals, grab the bounds, 0 to 2, and now you start putting things in. X is 2, y squared, t squared, dx, 0, plus x is 2, y squared, t squared, dy, 1. Right? Okay, now this is an integral where we actually get to do something. So this is the integral from 0 to 2 of 2t squared. Well, what does that integral become? 2/3 t cubed. Evaluate that from t equals 0 to t equals 2. And we end up with 16/3. And what do you get? So that's it. So if we're moving our object and we go first along C1 and then along C2, we do 16/3 amount of work. for all us engineers, that's 5.3333 amount of work. All right. So that's if we go and make that right angle. Your turn. What if you go in a straight line? What do you get? All right, do we have an answer? 8? Yeah. Now, I'm guessing that most people chose to do the parameterization t comma t. So just for fun, I chose 2t comma 2t. Just to say, look, I got the same answer, which is true. A different parameterization will give you the same answer. You just have to make sure you start and stop at the same place and don't jump back and forth, I suppose. All right, so we got 8. Now, you might notice something to help you see it. I computed what 8 is in terms of engineering, and these are not the same. They're different. And you're like, yes, they are. Why does that seem astonishing to you, Steve? Well, it is true that in general, we've just seen an example where we have this mdx plus ndy, where we had two curves that had the same start and stop, and they gave us two different values. So it's like, one way, if we think of it in phrased in terms of work, one way is less work if we move along that curve. But if we go back to Calc 1, we say, in Calc 1, we had situations where we wanted to integrate a to b of some function. And we said, if we found the antiderivative, we would just plug in the value at the end, subtract the value at the start. This right-hand side only depends on the endpoints. And if we want to get really fancy and start using language, which is going to show up, we'd say only depends on the boundary, what's going on at the ends. And so we see now that's not going to be true in general. But wouldn't it be nice if it were for at least some cases? In other words, is there some nice type of function where it does only depend on the endpoints, where we can get something like an antiderivative going on? And next time, we'll see that the answer is yes. For some nice cases, that's possible. All right, that's next time. That's it for today.